All right, so I guess I can start, right?
Yes, you can start. Yeah.
Yeah, cool. All right, so I want to start this talk by saying thank you to Professor Sauk and Professor Dr. Cheng for inviting me. It's my great pleasure to talk about our recent work on the crucial role of initialization for matrix factorization and LoRA in efficient machine learning reading group. This is a joint work with Liang Zhang, Professor R.M. Makhtari, and Professor Niao He. This talk will mainly about fine-tune language model with LoRA. I hope you guys have already know about LoRA. So this is kind of like one of the most popular approach for fine-tune language model with parameter efficiency. So the idea of LoRA is quite straightforward. So suppose that we have a specific linear layer and its size is n by n, right? And when I'm fine-tuning this specific linear layer, instead I will freeze it, and then I will add two smaller linear layers of size n by r and n by r on top of it. And when I'm doing fine tuning, I'm just like fine tune on the added layers, right? So in this way, I can reduce the trainable parameters from n by n to n plus n multiplied by r. And when this r is small, I can have great savings in memory and training time, right? So this is kind of like the idea of LoRA. And another reason for, that LoRA is really popular is that LoRA is make it very efficient to serve multiple downstream tasks. So for example, if I'm serving, let's say 5 different tasks in the traditional way, I have to store 5 different models, and each model have the same size of pre-trained language model, right? But with LoRA, I can just store a single language model, and I can store additionally 5 low rank adapters, which saves a lot of memories, right? So this is why LoRA is kind of like very popular these days. And because I came from a background of optimization, so what I cared about is more or less like the optimization of LoRA. And the optimization of LoRA is basically can be written in this way. So I'm minimizing XL and YL, and this subindex L means the L's layer. And this WL is just the pre-trained weight that I will freeze it when fine-tuning. So this is kind of like the optimization problem. But very unfortunately, directly optimizing it, at least studying it theoretically is quite challenging. So like there is actually no way for us to actually tackle this L layer thing. But the good part is that if we focus on a single layer, there is a way. And actually, like a single layer type of LoRA has been known under the name of Burrier-Monteiro factorization even before language model was invented. So the earliest literature that I know about BM was in 2003, and it was firstly used for solving semi-definite programming problems in a parameter efficient way. So the idea is quite similar. So essentially, if I cannot store a large matrix, I break it down to two smaller matrices, right? So essentially, break it down to XL and to break it down to X and Y's. And later, this BM factorization was kind of like get very popular in signal processing community, and the people have used it for matrix factorization, matrix sensing, and matrix completion problems, right? So given this literature, it is possible for us to kind of like track the optimization dynamic on LoRA applied on a single layer, which is kind of like this BM factorization or these classical problems. And this is like kind of like our main topic. So essentially, we will try to use a single layer LoRA to review the underlying optimization dynamics of LoRA and identify limitation and trying to address these bottlenecks. And the prototypical problem that we will talk mostly today is called matrix factorization. So matrix factorization can have like there are basically two different ways of formulating it. So if I'm coping with a symmetric problem, I can formulate it in the first equation. So essentially, this x is the variable that I'm trying to optimize, And you can see that it is already low rank M by R, right? This R is way smaller than M. And this asymmetric matrix factorization is more close to LoRA. So essentially I have two smaller matrices, X and Y, of size M by R and N by R. And I have like a matrix to be factorized, which is this A. And in recent literature, this matrix factorization is also known as LoRA applied on a single linear layer with whitened data. And the whitened data basically means that my data matrix, my data is just the identity. And to really understand what is whitened data, like it's a little bit complicated, and perhaps you need to read a little bit on this paper from Sanjeev Arora. But the thing is that there is an easier explanation. So essentially, you can think of my data matrix as an identity, and you can think it as like the one-hot labels. And this A matrix, the matrix to be factorized, you can think it as features, right? So essentially, like in the asymmetric matrix factorization problem, I'm solving an inverse problem. I'm fitting my one-hot labels to features, right? And the pre-trained weights, W0, you can think it as 0. So in this way, I think it is quite clear that this asymmetric problem is kind of like very related to LoRA. And most importantly, this asymmetric matrix factorization shares the same bilinear structure as LoRA, meaning this XY transpose structure is exactly the same. Perhaps the most important reason for adopting this problem as adopting matrix factorization as a prototypical problem for studying LoRA is that this problem is solvable using linear algebra. So basically, it means that we know where the global optimal is, right? But unfortunately, like optimization is never a great tool for solving this problem. I think most of you have already known that optimization is really struggling when dealing with saddle points. And you can see from this matrix factorization problem, x equals to 0 and y equals to 0 is a saddle point, right? And it actually have a lot of saddle points. So like that's why optimization really struggles when solving this problem. And another interesting behavior in optimization is that under different ways of parameterizing this problem, the convergence behavior can be quite different. So essentially, if my rank of x, meaning like this R, is equal to rank of A, I will call this problem exact parameterized, meaning that I'm using the exact number of trainable parameters to learn this problem. And when the rank of x is larger than rank of A, I will call this problem over-parameterized, meaning that I'm using additional learnable parameters to solve this problem. And similarly, you can define under-parameterization, right? So this is kind of like in different regimes, the behavior of the same algorithm can be quite different. I will talk about this in detail later. And there are some other small challenges for solving this problem using optimization. So the first one is that this is non-convex, right? Because it has saddle points, which we have already discussed. The second thing is that some of the really widely used assumptions in optimization literature does not really hold. The first assumption is like globally smooth, right? So essentially, this means that so basically, this smooth means the largest eigenvalue of Hessian is bounded. But if we check this simple two-dimensional problem, meaning that xy minus 1 squared, and we calculate the Hessian at x0, you can see that this Hessian scales with y squared. In other words, if my y is super, super large, the Hessian is no longer bounded. So for this matrix factorization problem, it is not really globally smooth. So this is the first challenge. And second optimization challenge is like the another property is called PL condition, does not hold as well. So PL condition basically because we have saddles, right? And once we have saddles, it means that PL does not hold globally. So these are like kind of like the smaller challenges for solving this matrix factorization or one layer LoRA problem compared with, I mean, like in optimization literatures. right? So this is kind of like our prototypical problem. And in this talk, I will basically show another interesting perspective for matrix factorization, or this one-layer LoRA problem. So basically, we will show that initialization is quite important for how fast the same algorithm is converging. And in the second part of this talk, we will apply the insights that we get from the theoretical derivation to fine-tune language models with LoRA. But before we really dive into our theoretical results, let's briefly recap the role of initialization in general optimization literatures, right? So if we go back to smooth convex optimization, we will basically see that the role of initialization hides inside this f of x0 minus f of f star. This f star means the optimal solution, and this f of x0 is kind of like the initial objective value. So in other words, like initialization basically means that how far away I am from my destination. And apparently, if my way ahead is too long, I need I need more iterations to convert to there, right? So this is kind of like the role of initialization in smooth convex optimization. And in terms of matrix sensing or matrix completion problem, which is more close to the problem that we are interested in today, there is another way, there is another role for initialization. So essentially, people have used the so-termed spectrum initialization. The idea is that I will initialize my x0 close to global optimal. And in this way, I can ensure locally I am smooth. So around my x0, my problem is smooth. And in this way, I can apply the theoretical results from smooth optimization one more time. So long story short, the theoretical understanding of initialization in optimization is kind of like limited and is mostly centered around how far is my initialization away from its destination, right? And if this route is longer, I need more iteration to convert to there. Kind of like a disclaimer here is that initialization actually plays some role when we are studying implicit regularization in gradient flow. But gradient flow is kind of like continuous thing, continuous optimization. So it's kind of like goes up beyond our scope today, right? Okay, so this is kind of like the role of initialization. And now let's get back to our matrix factorization problem. And for simplicity, I think in our talk, in my talk, I will mostly focus on symmetric problem. So essentially, the objective here is minimizing this problem, right? And although I'm only talking about symmetric ones, our discussion extends easily to asymmetric problems. But talking with symmetric problem, I can save some notation, and because like the insight is exactly the same, so I think this could be easier. And the workhorse for us today is not really gradient descent. It's actually like an optimization algorithm called scaled gradient descent, ScaledGD. And this algorithm is not super popular in machine learning community, but was quite popular in signal processing community because it converts really fast. And this idea is quite simple. So this is kind of like its update. So essentially like this eta is a learning rate. And this part, this xc transpose minus a multiplied by xt is just the gradient, right? And the preconditioner or the scaling part is this xt transpose xt inverse. And because like we are coping with low rank problems, like this preconditioner is only size r by r. So that makes matrix inversion acceptable. And actually, like this scale gradient descent has also been applied for training LoRA in a recent ICML 2024 paper. Okay, and now let's get back to the convergence behavior of this problem. So in the literature, we have known that when we are coping with exact parameterized problem, meaning the rank of x is the same as rank of a, we can get a linear convergence rate when I'm initializing x0 small. this small basically means that this x0 is just a Gaussian random matrix, but the standard deviation of this Gaussian distribution is quite small. It's actually very close to 0. And for overparameterized problem, meaning the rank of x is larger than rank of a modified version of scale gradient descent is also converging linearly, but the rate can only be established for let's say iteration up to 1000. And after this 1000 iterations, we do not know too much about the convergence, meaning that in other words, it means that we have to adopt early stopping. And for underparameterized regime, the convergence is actually unclear yet for some technical reasons. And now let's step back and re-examine this iteration. So in this case, we will actually find out that the scale gradient descent itself is actually a Gaussian-Newton method. To understand this, we can check this one-dimensional problem as squared minus 1 squared. Right? So this is exactly in the format of our symmetric matrix factorization problem. And if you write the Hessian out, you can see that this preconditioner is a kind of like approximation to the Hessian, right? So that's why like we call this scale gradient descent as a Gaussian-Newton method. But in optimization literature, we have known that Gaussian-Newton method can be faster than gradient descent. So that is actually the starting point of studying scale gradient descent, and that's why we want to ask whether it is possible for scale gradient descent to converge faster. After some derivation, what we find out is that the way to make scale gradient descent faster is not really on the Gaussian-Newton method itself. The secret actually lies in how we initialize this problem. So essentially, like to make it faster, I want to introduce this Nyström miniaturization. The idea is quite simple. It's just I initialize my x0 as a Nyström sketch of matrix A. Right? So this omega here is kind of like a Gaussian random variable with proper size. And for the exact parameterized setting, this omega is just the size m by r. Right? And interestingly, like the kind of like how because this omega is kind of like Gaussian random variable, like the standard deviation of this Gaussian random variable does not really matter for convergence. It can be super large. It can also be super small. Long as it's not 0, it's fine. And another thing is that I mean, even without direct access to A, like we can still initialize my x0 in this way. The reason is that we this A omega can be captured as a gradient computed at a very specific point. I believe that after calculating the gradient a bit, you can find this out, right? And the next question is that why Nyström miniaturization helps to get a faster rate. So the reason is kind of like threefold. The first reason is that with a little bit knowledge on matrix, on random matrix theory, we can show that x0, if initialized in this way, is rank R with high probabilities. And the second reason is that second and more important reason is that if I initialize x0 in this way, I can ensure this x0 and A, the matrix to be factorized, share the same column space. And I want to mention that this column space is actually the optimal column space, right? So this is kind of like the information that we get from initialization. And the third reason is that after do a little bit derivation, you can show that scale gradient descent. So basically every iteration on scale gradient descent xt share the same column space of A. So this is actually the secret of getting faster convergence rate with Nyström linearization. And with this intuition, we can formally establish the convergence behavior of scale gradient descent. It turns out that there is like a two-phase behavior. In the first phase, ScaledGD converges linearly from the starting point to a local regime, meaning that this xt1 is pretty close to optimal solution. And by the way, this kappa is a condition number of A. Right? So in general, it could be, let's say, 1000 or like 100. So it means that the first regime is converged linearly to a near optimal regime. And the second phase, after ending the phase one, right, we can get a quadratic rate when we are choosing our learning rates carefully. And in this case, we will directly convert to optimal solution in log 1 over epsilon iterations. So graphically, you can see from the left figure. So the x-axis here is the number of iteration, and the y-axis is the optimality error. And the orange curve is like a scale gradient descent with small initialization. You can see that it is converging linearly, right? And the green curve is scale gradient descent under Nyström initialization. You can see at the beginning it's kind of like converging linearly, but very quickly it goes to a quadratic phase, right? So this kind of like validates our theoretical derivation. And what is more interesting is the second figure. So in the second figure, all the solid lines are like scale gradient descent under Nyström initialization, but we are just using different Kasi for different color lines. And the dotted line is like we are using a perturbed Nyström initialization, meaning that we first get our x0 using Nyström initialization, and after that, we add a small perturbation matrix with Gaussian. We add a small Gaussian random variable on top of it with a standard deviation Kasi n equals to 0.1. In other words, this perturbation is quite small. And as you can see from this figure, before perturbation, I can get a quadratic rate. But after perturbation, the convergence basically slows down to a linear one, right? So this basically means that the role of initialization is really crucial for the behavior of the same algorithm. And in other words, this Nyström initialization actually gives me exponential improvement on how fast I'm converging. This is so much about exact parameterization. And in the over-parameterized regime, we actually show that a modified version of scale gradient descent has also similar convergence behavior. The modification here is that we use a pseudo-inverse on this preconditioner. The reason is that in the over-parameterized regime, meaning that rank of X is larger than rank of A, the preconditioner is not necessarily invertible. So that's why we have to use a pseudo inverse. And in terms of the theory, we can show that this modified scale gradient descent converges linearly, as you can in the initial phase. So as you can see in the left figure, so in the beginning, I'm converging linearly. And then after some iterations, it will get a quadratic rate similar to the exact parameterized case. And the second figure is conveying the same message. So essentially, if I perturbed my Nyström initialization a bit, the convergence rate, the convergence behavior of this modified scale gradient descent drops from a quadratic rate to I think in this case, it does not even converge. As you can see, these dotted lines are kind of like blowing up. So this once more demonstrates the crucial role of initialization. And in the under-parameterized regime, this is kind of like actually a more challenging regime because like some nice local properties is not cannot really be established. And that's why we are focusing on, I mean, in terms of the theoretical derivation, we are focusing on a relatively weaker optimality that we term weak optimality. The definition of weak optimality is defined in this way. So essentially my X transpose pseudo inverse of matrix to be factorized, and X equals to identity. Actually, you can show that all the global optimal are weakly optimal. So this means that whenever I'm converging to a weak optimal, there is still a chance that I retain global optimal. And in terms of function value, you can also show that in the worst case, weak optimal is not too far away from global optimal. And how far away from it, I believe, is scale with R to the 0.75th order. So this is kind of like, so in other words, weak optimality is not too bad. And under weak optimality, we can show that the convergence behavior of scale gradient descent under Nyström initialization is roughly like this. So essentially, if we are using a constant learning rate smaller than 1, we can get a linear rate up to a point that is close to the neighborhood of weak optimal. And the neighborhood has a radius scaled with eta, the learning rate, and r, the like parameterization. However, if I'm using a small enough learning rate, and basically let's say this learning rate scale with 1 over t, I can get a sublinear rate. But in this case, I can convert to exactly some weak optimal points. And in this figure, you can see that when I'm using a constant learning rate, let's say 0.1 or 0.2, I can convert linearly until an error of like, let's say 10 to the 0th order. And then after that, I cannot theoretically say anything, but empirically, you can see it is still converging. Right. So this is kind of like the theoretical results that we get. And to summarize our theoretical results, you can see the bounds in this table. This might be a little bit overwhelming, but the take-home message is that with Nyström initialization, the convergence rate can be significantly improved in both symmetric and asymmetric problems under different parameterizations, right? And in some regimes, the improvement can be even exponential, meaning that I'm converging quadratically instead of linearly. Right. So this is kind of like the crucial role of initialization. And now in the second part, I want to use the intuition that we get from a series, and I want to use this insight to guide our fine-tune procedure with LoRA. So what do we learn from our theoretical derivation? So essentially, like the directions are more important for bilinear structures or for BN factorization. So why? So essentially, like my Nyström initialization provides good directions, and these good directions are essentially the optimal column space of my optimal solution. Right. So with this prior, I can get a quadratic rate. Without this prior, I can only converge linearly. So that's why, like, direction is really important for my convergence. And if we write things out mathematically, so basically I can decouple my iterate xt in this way. So essentially, this u here is the kind of like the basis of the column space of my optimal solution. And this U perpendicular is kind of like the orthogonal complement to U. And it turns out that like learning this U, or actually the component xt1 is actually fast enough. But very unfortunately, learning this xt2 is very, very slow. And there is another work from iClear 2024 showing actually the same thing. But learning this xt2 is kind of like really, really small, really, really slow. And but the kind of like the problem is a little bit different. But the technical reason is essentially the same, that xt2 converts to 0 quite slow. So this is our intuition, like learning this direction is really important. And then basically like so essentially because learning this direction is slow, so that's why in practice we want to initialize my LoRa so that it is close enough to the optimal directions, right? So this is kind of like the message that we try to convey from our theoretical derivation. But the problem is that in LoRa, in fine-tuned language models, right, we do not know what is the optimal direction for the optimal solution. We do not know the optimal column space, right? But how can we achieve this? So the idea is that instead of searching for the global optimal, we can lower our expectation. And actually, like there is a line of recent works, including this SVFT in NeurIPS 2024, showing that there is a set of well-performed adapters, and these adapters have the same column space as the pre-trained weight. Right. So essentially, if our goal is not the global optimal, and our goal is just to find a good, some well-performed LoRa adapters, we can then just use like the column space of pre-trained weights to help my initialization. And the way we are like leveraging this column space is again to perform a Nyström sketch on top of pre-trained weights. And this is what we call Nyström initialized LoRa. It turns out that this simple strategy is quite effective in practice. And our first set of experiments is kind of like using this NoRA, Nyström initialized LoRa, to fine-tune a stable diffusion model. And this stable diffusion model have like almost 1 billion parameters, and we use rank of 4 for LoRa. And we apply this LoRa to the UNet part. And the goal of this fine-tuning task is to generate some images about a dog eating nachos. And by the way, this dog is kind of like a picture of the user himself. So very likely the stable diffusion have never seen this dog in the pre-trained data. And in the figures below, we show the generated images of different algorithms. So let's start with LoRa. It turns out that some of the dogs generated by LoRa is not really super clear. So for example, in this figure, you can see that this dog does not really look like a dog, right? And this LoRa P means like LoRa preconditioning, meaning that we are using scale gradient descent as the optimizer. You can see the image quality is relatively okay, but still in the third figure, this dog is not super like a dog, right? And this NoRA is just we applied Nyström initialization directly, and you can see that the image quality has already been improved. And this NoRA Plus is like we applied Nyström initialization on top of LoRa P. So in this case, you can see the dogs are also fine. But in both NoRA and NoRA Plus, you can see that there are some figures that does not really obey physical laws. For example, there is a natural that is floating. There is like a floating place. But this actually goes beyond the scope of the algorithm size. So we leave it for future work. And we also tested our NoRA on fine-tuned llama model. And we are using this common sense reasoning tasks with llama 7 billion and llama 2 billion. So essentially, we are using less different data sets, and we mix all the training data of data sets together, and we test them separately. And in terms of LoRa, we are using R equals to 32, and this actually leads to 56 million trainable parameters, and the result is shown here. So again, like with NoRA, like the performance is actually better than LoRa itself. This means that Nyström initialization actually helps a lot. And when we are comparing NoRA Plus relative to LoRa P, we can also see some like gain, some performance gain, right? But the gain is actually like not as significant as NoRA versus LoRA. Right. But considering that this initialization is kind of like just some matrix multiplications that I have to do in the first step, so we consider this performance gain is almost like a free lunch. Right? So that's why like we still encourage people to use this initialization in practice. And to conclude, in this talk, we've talked about initialization exponentially impacts the convergence of scale gradient descent on matrix factorization problem. And we use matrix factorization problem as a prototypical problem for studying LoRA theoretically. And we use these insights to really guide the fine-tuning procedure in practice. And there are more details of this talk in our paper, in our iClear 2025 paper. And to go maybe a step further, right, because we have mentioned that learning the optimal directions is a bottleneck of BM factorization. So that basically means that if we are not using BM Bury-Montero type parameterization, there might be a chance to get over this problem. And it turns out that this claim is true. And essentially, if you are using a modified version of SVD parameterization paired with remaining optimization, you can you can solve this slow learning of optimal directions. And this you can find more details of this new structure in our recent paper, Polar. And regarding future directions, I think it's quite important to extend our theoretical results from this minimal LoRA example to more general cases. And another interesting direction is that we should somehow dig more prior out of the pre-trained model, such that we can better initialize the structures that we are using for fine-tune. I think that is kind of like all I want to share about. Yeah, and thank you. And if you have any question, I'm happy to answer